Hello, my name is Patrick, and today I'll talk a bit about our Centerstage robot's outtake design process. So starting from kickoff, we did a lot of brainstorming. So first, we set some objectives for what we wanted our robot to do. More specifically for our outtake, we wanted to have fewer degrees of freedom, so that it would be simpler to build. So looking at how the backdrop is angled at a 60-degree angle, we wanted to also transfer pixels already at a 60-degree angle, so that there would be no claw pitch degree of freedom or axis needed. So that means we can just directly lift the pixels up and out. So you can see kind of our intake, or this is our V1 design, but our intake does transfer the pixels at a 60-degree angle, and you can kind of see this side view. Another objective we wanted was compliance, which means that the claw should be able to compress against the backdrop. So that means the drive base can be a little bit off or not as precise. And this means that the driver can drive a lot quicker and doesn't have to aim as well. And this should also help to reduce descoring pixels, because knocking the backdrop at too high of a speed can result in pixels falling off. So given that we wanted to have this type of compliance, it was easier to use horizontal sides instead of something like a virtual 4-bar. Because the virtual 4-bar, it's a little bit harder to implement compliance into it, because if you're extended, then it'll just be a bit more difficult to work with. Finally, another objective was optimization. So to do that, we wanted to reduce the footprint of the pixels. So we stacked the 2 pixels on top of each other, like you saw in the intake magazine image. And then also to reduce mass, we only have 1 servo to drop the pixels separately. So here's a image of the 2 claws, and you can kind of see that the top one is driven directly by an axle, while the bottom one is basically dead axle and it's free to move. So from September to October, we worked on our CAD. So the overall process for this is basically we already had the drivetrain and intake done and CADed. So what we need to do now is insert large components such as our slides, and also compare the positions of where we want them relative to the rest of the robot. And then in doing so, we can connect the components using, for example, this piece right here connects the horizontal side and the vertical sides. You can see there's a sketch over here that kind of shows where the claw would be if it was extended. And of course, this is a very final version. It definitely didn't look anything like this in the first iteration. So one of the biggest challenges with the outtake design was the linkage position, because we have a lot of other subsystems inside the robot that we don't want to hit, and at the same time, there's a lot of other requirements that we wanted it to satisfy. So for example, we had this angled top of the robot, or this like L shape on top is the outer perimeter of the robot. This is a side view, and then we had this angle thing so that we can lift up the stage door, so we can't have the linkage extending out of it, or else the linkage itself would hit the stage door, and that would be really bad. And then we also have this over here, the other axle for our climb mechanism. And then we also sketched out this intake, or a very brief sketch of an intake, so we can figure out where we want the claw to be and where we want it to go. So we did linkage positioning. It took a lot of trial and error. So you can see first we tried like a more traditional type of linkage, but this linkage was too tall and it exceeded the top of the robot, so that was not good. Our next try, this was slightly better and closer to our final design, but this would collide with the climb mechanism. Third try, this is just not feasible because it kind of collides with the entire intake. So, but you can kind of see where this idea for like the first arm going all the way backwards, like past the point of revolution idea came from. So this would allow the linkage to be much more compact. And so this is our final design, where the servos above the slides, and then the linkage goes below the slides, kind of like this. So after that, it was pretty straightforward to design the rest of it. So some tips for like designing complex things like this. Basically, you want to think in 3D, but draw stuff in 2D. So you can see in this sketch over here, there's a lot of there's the intake right here, and then there's kind of the claw shape and the claw fingers. So these things don't appear in the same plane as this plate, which is the claw's side plate, but but I kept them in mind as I was designing this so that you can make sure where to place things correctly. So from November to December, we did a lot of assembly and a lot of testing on V1 Outtake. Yeah, we won't show that because there's nothing very interesting. So in January to February, we participated in qualifiers and regionals. And so here from this real competition experience, we found a lot of issues with the Outtake. So first thing is you can see here that even with the compliant Outtake, it still hits the backdrop a bit too hard, and it knocks some pixels off during autonomous. So that was the main issue, which was why we redesigned to V2. So of course, the first issue was that the robot was too close to the backdrop during autonomous. And so what that meant is that the drive base itself would hit the backdrop, and that would kind of just knock pixels off. So what we needed is a longer extension so that the drive base isn't anywhere close to the backdrop itself, so that it wouldn't hit. Issue number 2 was that the linkage would hit some things at the bottom of the robot. So our linkage would hit kind of the bottom plate of the robot because it was too long. So then what we wanted is a linkage that goes from above the slides, and combined with the fact that we need a longer extension, the only possible linkage that we can use to get such a long extension is a double reverse 4-bar. So you can kind of see your initial thoughts and considerations for how this double reverse 4-bar linkage would work. And the nice thing about double reverse 4-bar is that compacted, or it's very compact when you retract it, and overall it gives you about 4 times as much extension as one of the arms over here. So using that, we started some more linkage position trial and error. So yeah, the reason why there's 4 gears over here is because when we retract it, we want the 2 ends of the linkage to be just far enough apart, just exactly right, to have them stay still on the other side. This is a bit hard to explain, but either way, we needed the extra 4 gears to extend the top bar's length, like this right here, so that the linkage positions would work out better. So we also did a 3D print prototype because this is a very complex linkage, so it needs a lot of testing. The video is a bit bad because filming with one hand and operating something with another hand is a bit difficult to do, but you can kind of see how it works. So again, there were also this is a third issue that we wanted to resolve with V2, which is that when we dropped at an angle, even dropping at angles above 15 degrees in the original design occasionally caused some pixels to fall off of the backdrop. So this rotational compliance over here, which we covered during behind the bot video, is able to basically let the robot drop from even 45 degrees or something like that, because the claw itself holding the pixels will always be flat against the backdrop. Again, we can look at the behind the bot video for our final V2 features. But yeah, for now, are there any questions?
Thank you so much for that presentation. It looks like we have a question online. Why did you use a linkage for the linear slide instead of rigging it?
All right, so basically, we kind of ran out of motors. So basically a servo linkage would be easier to do than having another huge servo with like a huge pulley. Basically it's just simpler to do the linkage instead of like doing all of the like rigging with string and everything.
Okay,
Okay.
sounds good. And then we have some other few questions in the chat. How much physical prototyping did you do, or was it mostly just in CAD?
Yeah, so there was basically no physical prototyping for the outtake. Everything was in CAD. I guess we could consider the one prototype is the V1 version. So yeah, kind of the V1 version kind of was a prototype for V2, but again, there was not really much physical prototyping.
That sounds good. So do we have any in-person questions?
Makes the thing durable and like not just hold weirdly.
Did you catch that question?
Could you repeat that?
How did you make it durable and not fold weirdly?
Like which part of the outtake or
Which part I'll take? The linkage.
I mean the linkage itself is so I mean like in terms of making the linkage rigid, basically these like arms over here, these bars are actually two parallel carbon fiber plates, so that just makes it really rigid. Like almost everything on this linkage is like parallel carbon plates, so like it should be pretty sturdy, if that answers your question.
Okay, great. I think it does answer this question. Thank you, Patrick and Hyperion for this presentation. It looks like there's some unanswered questions in the chat, so if you want to just answer those, that'd be great. And yeah, let's give him a round of applause for Hyperion.